Hi everyone, again, thank you all for being here today, and also thank you to my committee members to agreeing to be a part of my committee. I appreciate your time and support. I'm Ilkin Isler, and I'm a PhD candidate at UCF, and as Dr. Mohaisen mentioned, I'll be presenting my dissertation defense, Advanced Deep Learning Algorithms for Medical Imaging Applications with a focus on tumor and organ at risk segmentation. So I started my PhD in 2020, and my advisors are Dr. Turgut, Dr. Mohaisen, and Dr. Baje. Along the way, I completed my master's in 2022, and before that, I finished my undergraduate degree in Turkey in 2020. My research interests are in deep learning and computer vision with a focus on high-risk applications like medical imaging. Here's a brief outline of my dissertation. So we will start with the introduction and background to provide context on why this problem is important and also highlight the current challenges. Then we will move into the core of the work, which is a proposed family of deep learning algorithms tailored for medical imaging. So I'll begin by covering uncertainty-aware segmentation algorithms. After that, we will get into analysis of the data we are using and how uncertainty is crucial for medical imaging, and also the correlation between data and the models that we are using and their performance. After that, I'll transition into classification algorithms for outcome prediction, and finally, I will conclude it with the impact of my dissertation. So let's start with the introduction and background. Before we get into the methods, here's a quick look at what segmentation is and why it matters. So it's essentially pixel-level labeling, assigning a class to each pixel, and it's key for tasks like identifying tumors or organs in medical images. We have seen big strides in segmentation, like Meta AI Segment Anything, but these general models don't perform well in medical imaging due to issues like low contrast, data scarcity, and high anatomical variability. Medical segmentation is very challenging due to limited annotated data and both inter and intra-subject variance, which means that we can get different segmentation masks from different oncologists for the same patient, and we can even have the same person create two different segmentation masks the same day. So we don't really have a true ground truth. Existing models are not yet robust enough for reliable clinical deployments, and errors in segmentation can directly affect diagnosis accuracy and treatment planning. So the aim of this research is to fill in those gaps and develop segmentation algorithms that are more reliable and clinically relevant. In addition to segmentation, my research also focuses on classification algorithms, which are equally important in the medical imaging domain. These models are used for tasks like early diagnosis, prognosis, and risk stratification, where the outcomes directly influence critical clinical decisions. For example, the image on the right shows a pancreatic MRI from a patient with IPMN lesion. The goal here is to classify the lesion into one of two categories, low risk or high risk, based on the imaging and potentially other features. And getting this classification right is essential because it can determine whether a patient gets routine monitoring or they need urgent surgical intervention. So the aim here is to develop robust and generalizable classification algorithms. The overall goal of this dissertation is to develop AI-driven medical imaging algorithms that can enhance cancer diagnosis and treatment. And to achieve this goal, this work focuses on several key directions. First, we propose an uncertainty-aware segmentation framework to improve the accuracy and the reliability of tumor and organ at risk segmentation. Second, we explored the integration of self-supervision to pre-trained segmentation models to improve robustness, especially in areas like medical imaging. We have low data, so the annotations are sparse. And third, we work on improving 3-year survival prediction in lung cancer patients by combining deep learning models with radiomics feature to bridge the gap between imaging and patient-level outcomes. And finally, we aim to enable automated quantification of pancreatic cysts to support early diagnosis, which is critical for patient outcomes. So our work includes new algorithms for both segmentation and classification. We focused on two major cancers, lung and pancreatic. Lung is the top cause of cancer deaths, and pancreatic has just a 7% 5-year survival rate in the United States. So these cases pushed our models to show how well they generalize. For segmentation, we use uncertainty-guided methods to segment tumors and organs at risk, which is crucial for radiation therapy planning. And for classification, we predict 3-year survival in lung cancer and assess the risk levels for pancreatic lesions to help identify high-risk cases earlier. And by addressing both treatment planning and early diagnosis, we show that our approach works across different organs, cancer types, and clinical goals. So let's move on to the second chapter, organ at risk and tumor segmentation with uncertainty quantification. UNet is a well-known deep learning model for medical image segmentation. It works well even with small data sets, which is great for medical imaging where labeled data is limited. Its U-shaped encoder-decoder design with skip connections helps capture both local and global context effectively. And I will briefly summarize 2 of our published works and give more details later on our latest work. So starting with this one, the goal here is to improve segmentation accuracy for both tumors and nearby organs using simple but effective changes to standard deep learning models. We fine-tuned core components like the loss function, optimizer, encoder, and normalization, and small adjustments here made a big difference. Our model achieved an average dice score of 80%, clearly outperforming the baseline UNet at 63%. And on the right, you can see visual results from 3 different data sets. Our method delivers cleaner and more accurate segmentations. And this work was published in SPAE Medical Imaging 2022, and it laid the foundation for more advanced methods I will get into next. In this work, we built on our previous research and added tumor segmentation. Radiation therapy is widely used for cancers, and while it's effective, it requires high precision, and that's where segmentation becomes critical, so radiation hits the tumor and not the healthy tissue. And we wanted to test whether self-supervised pre-training on transformers could improve the segmentation performance. That led us to develop our own model, MC-SVNU, which is a Monte Carlo transformer-based unit. Our method improves accuracy, reduces the need for large annotated dataset, and even gives insight into uncertainty. And this work was published at IEEE ICE-CCME 2023. Before we dive in, I want to quickly explain a couple of clinical terms and why segmentation matters. OAR stands for organ at risk. These are the healthy organs near the tumor that we want to avoid during radiation. GTV is the gross tumor volume, basically the visible tumor seen on the scans. Inaccurate segmentation helps target the tumor while sparing healthy tissue for better outcomes and eventually fewer side effects. So in short, we need to segment both the tumor and also the nearby organs, which are organs at risk, to make treatment safe and effective. All right, so let's take a closer look into the current landscape. Segmentation for radiation therapy today is manual, which is slow, expensive, and often inaccurate, which is risky in such a high-stakes setting. It usually takes several hours per case, and from diagnosis to the actual treatment, there's often a 10-day gap, and during that time, the tumor itself can change. They're not static. So if we could speed up segmentation with deep learning, we would be able to update the segmentation mask dynamically and closer to the time of the treatment and adapt to changes in the tumor. So that's the motivation behind our work. We explored how self-supervised transformer pre-training can improve segmentation. So let's break down some of the key parts of our study. First, we use deep learning for tumor and organ at risk segmentation. making the process more accurate and cost-effective. Second, we apply self-supervised pre-training, which means that the model learns from unlabeled data, and it helps reduce annotation needs and also improves generalization to new cases. Third, we use transformers. So unlike CNNs, they process images as patches and capture both local and global relationships. And this is great for understanding how tumors and organs relate spatially. And finally, we incorporate uncertainty. So by estimating a confidence here, we make the model's predictions more transparent to help clinicians trust and also adapt the system easier. So these 4 components form the foundation of our work. Here, I'll walk you through our proposed MC-SWIN-U architecture. So we start with a SWIN unit R backbone, and we modify it by adding dropout layers for uncertainty quantification, which I will explain in a second. And we have weights of a self-supervised pre-trained SWIN transformer trained on over 5,000 CT scans. We then fine-tune it for tumor and organ at risk segmentation using our labeled data. So this model takes in 3D CT images and converts them into 3D tokens through a patch partitioning system. More on that in the next slide as well. And at test time, we keep the dropout layers active, which gives slightly different outputs for the same input. And these variations, called Monte Carlo samples, let us estimate uncertainty, which serves as a guidance tool for clinicians. And here's a more detailed view of our architecture. The input first goes through a patch partitioning system, then into the SWIN transformer blocks. And the decoder follows a typical unit structure with upsampling and skip connections. And the features are extracted through multiple layers and passed to the CNN-based decoder. And the final output consists of 6 segmentation channels. So for this research, we used 2 data sets. The first one is NSCLC radiomics. It's a public set with thorough images from 133 patients. The second one is a private data set from Orlando Health with images from 144 patients. Both data sets include patients with non-small cell lung cancer, and they come with ground truth labels for the lungs, spinal cord, esophagus, and gross tumor volume. One thing to notice here is not all segmentation tasks are equal. Lungs are large and consistent, so it makes it easier to segment, and tumors are harder. They vary in shape, size, and location, and that's what makes our work meaningful. It tackles some of the hardest and most variable cases in real-world settings. Here are some results from both data sets. The first column is the CT image, second is ground truth, and we have the prediction without and with our proposed method. And our model shows more accurate predictions, especially around the boundaries, which are typically the hardest areas for deep learning models. The zoomed-in uncertainty maps on the right show non-red areas as uncertain, and as you can see, the model is mostly uncertain at the edges, which is valuable feedback for clinicians when reviewing the masks. In segmentation, higher dice and lower Hausdorff distance mean better performance. And what we found is that self-supervised pre-training helps the most in hard-to-segment areas like complex lung tumors, and it also speeds up development. And with this approach, we saw notable improvements, 1.6% dice on our public dataset and 1.1 on our private dataset. These may seem like small gains, but in medical image segmentation, even small improvements are clinically meaningful, and they show we are moving in the right direction. On top of that, providing uncertainty gives us deeper insights. So we will talk about our recently accepted work to IEEE ACDSA on lung tumor segmentation. This is a 2-stage coerced to fine approach. On stage 1, a full CT model produces a coarse segmentation, and that output goes through a post-processing module which merges nearby components and then applies anatomy-based filters, then selects the most likely tumor regions. Those selected areas are then cropped and passed to stage 2, where a separate ROI model performs fine segmentation. And in this second stage, we keep dropout layers active during inference to estimate uncertainty, which helps interpret model confidence, especially near the edges. Here we show 4 patient cases. The top row is the raw CT. The tumor area isn't obvious at the first glance. The second row is the expert annotation in red, which we call the ground truth. The third row is the model's initial prediction. You can see extra specks and rough borders here. And then the fourth row is after our lightweight post-processing. The mask lines up much more closely with the ground truth, so the false positives disappear and the shape tightens. The bottom row is a close-up to the tumor with the uncertainty map overlaid. The dark purple here means high confidence and yellow means the model is unsure. And as you can see here, uncertainty peaks around fuzzy boundaries where the tumor blends into healthy tissue. And the results show that our post-processing cleans up the raw output, and the uncertainty heat map highlights exactly where the model is least confident, which is useful for flagging tricky regions. So let's walk through the 2 main points on this slide. In our loss function comparison, the top table, DICE CE wins on numbers, but when we look at the outputs visually, we see that the uncertainty guidance variant delivers clearer boundaries for clinical review. And in the bottom table, using only the largest component, the top one, gives us the best DICE and the lowest Hausdorff distance 95 score. And when we include top 2 or all components, it introduces false positives. And on this slide, we are comparing our pipeline to the baseline across 3 architectures on both private Orlando Health and public NSCLC dataset. In every setting, our proposed method boosts DICE over the baseline, and the largest gain we see here is for SwinUnit R on Orlando Health dataset. So the ROI cropping plus top 1 filtering and uncertainty modeling consistently yield to cleaner and more accurate masks across all different network architecture without any extra computational costs. So now let's dive into the data analysis. We will look at how uncertainty plays a key role in medical imaging and also how the data characteristics relate to the model performance here. So even strong models struggles with some tumors. So we analyze model confidence and tumor features like texture and intensity. The goal is to spot high uncertainty and low performance cases, the ones that we won't want to flag for human-in-the-loop review. And most algorithms technically work, but they aren't used in clinics because they lack trust. And that's what we are aiming to solve by predicting where the model might fail and involving a human when it matters. We analyze 2 feature types. One is the custom and the other one is radiomics features. The custom features included tumor size, contrast, edge complexity, and shape metrics like compactness and sparsity. They are simple, intuitive, but possibly limited. And radiomics features captured texture, shape, and intensity commonly used in oncology. And our aim is to see if these features relate to segmentation difficulty and whether high uncertainty, low performance cases show distinct radiomics patterns. And here, let me walk you through how we evaluate segmentation and why we need uncertainty-aware and margin-tolerant metrics. So the dice similarity coefficient is commonly used. It measures the overlap between prediction and the ground truth, but dice doesn't show where the errors are. That's why we also use Hausdorff distance. It captures boundary errors, but the standard HD is too sensitive to outliers. So we use HD95, which ignores the extreme cases and gives a more stable boundary measure. Together, dice and HD95 provide a more complete picture, volume overlap plus the spatial accuracy. That said, even these aren't perfect. In clinical practice, small boundary disagreements often doesn't matter, but our current metrics penalize them anyway. That's why we need metrics that reflect clinical relevance, ones that are uncertainty aware and margin tolerant, which means they are tolerant to small and non-critical errors, especially in the cases where even the experts disagree. Here's a distribution of custom tumor features from the cropped ROI data from Orlando Health dataset. And the tumor volume and diameter are right skewed. Most are small with a few large ones. Next, contrast is skewed low. Many tumors are low contrast, making segmentation harder. And for edge complexity measured by the Kenny count is low, likely because we removed background anatomy. And for shape compactness, clusters around 1,000 to 2,000, and sparsity shows a bimodal pattern. So some tumors are spherical and some others are irregular. Now looking at the full CTs, the size and shape features stay the same as they describe the tumor itself only, but contrast and Kenny edge shift a little bit, likely due to more surrounding tissue and background noise. In this extra context can help with localization, but it can also add complexity, which comes from the edges from the ribs, vessels, etc., and that can confuse the model. And these shifts help explain why segmentation behaves differently on full CTs versus the cropped ROIs. So these heat maps here compares how tumor features relate to segmentation performance in both cropped regions and also the full CTs. Here's a few takeaways. The tumor size correlates with performance in full CTs, but not in cropped views. And that tells us size helps with localization, but not boundary accuracy. Another one is contrast and edge complexity show a similar pattern. It's more helpful in full images than crops. Another one is dice and Hausdorff distance correlate strongly, and it makes sense because better overlap means cleaner edges. And overall, full CTs benefits from size and contrast, and crops rely more on subtle shape or texture, which could explain shifts in performance. So let's see if these custom features explain segmentation performance here. I plotted the dice scores from the cropped tumor model against each of the features. We see weak trends like larger tumors or complex edges slightly linked to lower dice, which tracks with harder cases, but overall none of the features clearly predicts performance. Here's the same exact analysis, now using dice scores for the full CT model. We still see weak trends, mostly with volume and compactness, but more variability overall, and this is likely due to the background noise, multiple lesions, or missing context. And these features offer some insight, but not enough to explain why some tumors are harder to segment compared to others. And that pushed us to explore more expressive features, so we turned to radiomics, which are more detailed and also commonly used in oncology. So these radiomics features include shape metrics like elongation and surface to volume ratio, and texture metrics like entropy and run length non-uniformity. And our goal here was to see if these features could explain model performance or highlight the cases with high uncertainty. On the left, we saw the Pearson correlations for linear trends, and on the right, the Spearman for nonlinear ones. And for example, features like elongation and surface to volume ratio were moderately correlated with both Dice and Hausdorff distance 95, which suggests that irregular or elongated tumors tends to be harder to segment. So here we found that tumor shape, contrast, and edge complexity significantly affect segmentation performance. In particular, high uncertainty was linked to low contrast and irregular shapes. Some radiomics features show better ability to predict performance than the traditional features, helping identify difficult cases. In comparing full CTs to ROIs, we saw that feature impact changes by context, but ROIs provided more focused and reliable insights. So overall, these findings are valuable for quality assurance, uncertainty over triaging, and human-in-the-loop systems, where flagging the challenging cases early can improve the reliability. Now onto the outcome prediction, where we're tackling two problems. One of them is the 3-year survival analysis of lung cancer patients with CT images, and the second one being risk classification for pancreatic cysts with MRI images. So we start with survival prediction. The goal here is to improve 3-year survival prediction, which is a critical step towards personalized treatment planning. We explore two complementary types of features. First, the deep neural network features, which we extract from a DenseNet 1-to-1, and these capture complex and abstract patterns from the medical images. Second, the radiomics features, which offer more interpretable information that help quantify tumor heterogeneity and structure. And our approach here is to fuse these two feature sets so that we can leverage the strengths of both. And this fusion here improves the model robustness and gives us richer and multi-scale representation of each patient's data. After extracting the features, the next step is to select the most informative ones to reduce overfitting and speed up computation. So for that, we use two different methods. PCA, which reduces the dimensionality by transforming the features into an uncorrelated components that retain most of the variance, and also lasso, which adds a penalty to keep only the most relevant features. Then we use SGBoost for the classification task, which is a powerful gradient boosting algorithm that works really well on structured data like our extracted features. So it is also interpretable, which is important for clinical trust, and it can handle nonlinear relationships effectively, making it a great fit. So here's a full overview of our pipeline for predicting the 3-year survival. At the top, we have the DenseNet 1-to-1 model, which takes CT images and learns deep features directly related to survival outcomes. Simultaneously, we extract radiomics features from the same CT scans using the clinical GTV masks, and this includes shape, texture, and intensity-based descriptors that give more traditional and handcrafted insights. Then we apply feature selection to reduce redundancy and keep the most informative deep learning features. And these selected features, both deep learning and radiomic ones, are fused together and passed to an SGBoost classifier. And this model predicts a binary outcome, whether the patients survive at the 3-year mark or not. I want to highlight something important here we explored. So instead of just using GTV, we also looked into the paired tumor region, meaning the area right around the tumor. So here we have the GTV alone. In the middle, we have added the 4mm margin around the tumor. So this is the GTV plus the surrounding tissue. And on the right, we isolated just the paired tumor region. And here, paired tumor regions can carry extra predictive signals, especially for survival. So combining features both from tumor and the surrounding tissue improved accuracy, and it showed us that the context beyond the tumor itself actually matters. And finally, here the ablation study for this work that shows how each feature set contributed to our classification performance. We started with radiomic and deep features separately, and the performance was modest. In adding the DNM features improved the results, but the biggest gain came from including this paired tumor region. And as shown in the last row, combining GTV and the paired tumor radiomics with deep features gives us the best accuracy, supporting the hypothesis we had. So here I will talk about an extension to this work. After the committee feedback in my dissertation proposal, we switched from binary classification to a Cox model for continuous survival times. And we now extract deep features using our pre-trained SVNUnet instead of our DenseNet and combine them with radiomics, follow-up time, and event status. So 1 corresponds to that and 0 for censored, and we drop any constant or infinite columns. For the neural Cox-PH model, we still use a 3D DenseNet 1-to-1 backbone to output 1 log risk score per patient. And then the training here minimizes the negative log partial likelihood, which means that the uncensored patients drive the numerator, while censored cases stay at the risk set, but they don't count in the numerator. And this way we leverage full time to event data instead of forcing a binary outcome. So we compare radiomics only, SVNUnet R only, combine early fusion and also late fusion. And here late fusion gives us the highest concordance. Now we will talk about pancreatic cancer, which has the worst prognosis in the United States. That highlights the urgent need to come up with a better early detection. And in this work, we focus on IPMN cysts, which are the pre-malignant lesions in the pancreatic duct that can turn into cancer if untreated. And early detection here is the key. We use MRI scans to extract features for quantification and risk classification, and our dataset has over 300 patients. Our goal here is to support earlier and also more confident risk classification for clinical decision making. So you can see examples of cysts in the head, body, and the tail of the pancreas in these pictures. This slide outlines the risk stratification pipeline for pancreatic cysts. So we start with the raw pancreas MRI and its segmented IPMN mask to isolate cyst and pancreatic tissue. And from those images, we extract 3 types of features. One of them is the radiomics descriptors for the cyst region. The second one is the deep CNN features using our risk CNN. And then the third one is the pancreas to cyst volume ratio as a simple volumetric biomarker. We then apply PCA for dimensionality reduction to prevent overfitting. For this, we picked 30 components per modality or 50 when fused. And finally, an SGBoost classifier takes the reduced features and outputs a binary label. So here, 0 for low risk and 1 for high risk. Here's our performance table for pancreatic cyst risk models. We found that using a reduced radiomic set, which means just shape and first order features, cut the noise and improve the AUC. We also see volumetrics only gives similar results as radiomics. Another thing we noticed is extracting both dense block 3 and 4 improve AUC. And since dense block 3 preserves fine texture and dense block 4 captures more of the higher level features, early fusion of all features yielded to AUC 0.62, while normalizing per source improved AUC. And the best results came from late fusion, where each model's classifier votes. And to summarize my dissertation, My first author accomplishments include 3 projects. Our latest work, uncertainty-guided coarse-to-fine tumor segmentation with anatomy-aware post-processing, which was accepted to ACD-SA this year. Self-supervised learning for organ at risk and tumor segmentation with uncertainty quantification, which was published in IEEE ICE CCME 2023 and presented orally. In our paper on improving deep learning neural networks for organ at risk segmentation, which was published in SPAE Medical Imaging 2022. As a co-author, I contributed to 2 additional projects, one on multicenter CT and MRI segmentation of the pancreas, recently published in Medical Image Analysis 2025, and another one in Practical and Ethical Considerations of Generative AI in Medical Imaging, published at MICAI 2024. My dissertation contributes to 3 key areas of clinical impact. First, it supports improved early diagnosis. So by incorporating uncertainty, shape, and text features, the algorithms I developed can flag suspicious regions more reliably, and even when they appear subtle or ambiguous on scans. And this can help detect tumors earlier and reduce the risk of missed diagnosis and eventually save lives. Second, it enables enhanced treatment planning. Right now, in many clinical settings, outdated segmentations are reused across time points, and even when the tumor has clearly changed in size or shape, this can lead to suboptimal treatment, especially in high-risk cases like radiation therapy, where dose planning relies heavily on accurate tumor boundaries. And automating this process with accurate, uncertainty-aware segmentation reduces the risk and ensures that treatment is aligned with the current state. Finally, this work supports better outcome prediction and prognosis. And overall, this dissertation introduces algorithms that can minimize human error, reduce clinical burden, and ultimately improve patient outcomes, especially in time-sensitive and high-stakes scenarios like cancer care. And thank you all for your time and attention. And before we dive into your questions, I would like to quickly revisit one Dr. Zhang asked at my proposal. Thanks to him for raising it. I now have a clearer answer that I want to talk about. The question was, can we use spatial transcriptomics instead of 3D CT MRI for tumor segmentation? And this means like the 10x Visium or Xenium. Here are a few things that I would like to address. So first of all, it generates ultra high resolution 2D images. So it lacks the volumetric context essential for the 3D segmentation in CT and MRI. And staining adds variability and also huge file sizes that causes high computational complexity. And another thing is like molecular level data typically calls for multiple instance learning and survival analysis tool rather than the standard 3D segmentation networks. So in the future, we could fuse both data types, but it would need new pre-processing and models. And with that, I'm happy to take any of the questions that you might have.
Awesome. Thank you so much, Ilkin. Let's first ask the committee members. Let's start with people online. Let's start with Dr. Zhang, Wei Zhang. Do you have any questions?
Yeah. Thank you. I think it's a very nice work, and then thank you actually for addressing my questions from the dissertation proposal separately for the spatial transcriptomic data. And then I have two questions here. One question is that for the spatial transcriptomic data, have you thought about actually the segmentation, because it's a very high resolution, they can segment the cells, and then the thing that probably your models can be applied actually to ROI, the region of interest that actually have a group of cells, and then you, instead of do the region segmentation, you can do the cell level segmentation there.
Yeah, that's actually a really good point. That's also what I thought. So since we don't have the volumetric context, But if we were to find the location of the tumor itself, we can locate that in these high resolution images. And also, if we only get the crop, the computational complexity wouldn't be that high. So that's definitely a way to combine them for the future work.
Okay. Yeah. Another question is that why do you need to customize the features there? So that part I still don't quite understand, because you can let the model actually to do some actually not the like the feature selection, or actually to do the dimension reduction to learn the embeddings from data itself, instead of to customize the features. So could you please provide some more background about that part?
Of course, yeah. So we can basically just use a neural network, and we would normally expect the neural network to pick the most important features for us. But in the cases where we're doing outcome prediction, we need something more explainable. So we want to be able to have a control over the features that we are selecting. And by using these models, we can also see, okay, these features affect the outcome by this percentage. So that is why.
Oh, okay, I see. Yeah. You want the explainable actually features instead of actually some like the hidden dimensions there, right?
Yeah,
Hidden dimensional
exactly.
features. Yeah. Okay, I see. Thank you. I don't have any additional questions here. Yeah.
Thank you so much.
Thank you, Wei. Let's go to Dr. Leo Cortes. Go ahead. You have any
Yes, thank you. Thanks, Ilkin. I really enjoyed the presentation. First, I really liked the fact that you went back and the correlation matrices to show which observable features and how did they relate to the accuracy of the segmentations. I thought that was really nicely done in the document and in your presentation. So thank you. I would like to ask about ask you to redescribe again a little bit the difference between your your early fusion and late fusion that you mentioned in there. It showed that late fusion had better results. Just if you could tell me that procedure again a little bit, what you mean by what order the things were bound in there in the early and late fusion.
Of course. For the survival modeling or for the pancreatic risk one?
This one that you have here displayed, the survival modeling would be fine.
Of course, yeah. So for the early fusion, what we are doing is we have two different sets of features, one coming from the radiomics features and one from deep learning features. So their dimensionality is so different than each other. The deep learning ones are higher dimensionality. So if we were to not normalize them or like fuse them earlier, and then use a classifier, the classifier is going to choose whichever features it wants to use. But since it doesn't really match with each other, we can end up with only radiomics features or only deep learning features. But if we're using late fusion, we are going to get an answer from two different feature sets. And then what we're doing is we are using those two outcomes and then using them as a tool to predict the outcome.
Okay. So yeah, so running like the XGBoost or whatever on, for example, the radiomics features only, and then on the deep learning features only, and then ensembling the answers of those multiple models for the late fusion. Okay, that makes sense. Thank you.
Thank you.
Any other questions?
Just that I was pleasantly surprised that the paratumor region had such a positive effect on the classification accuracy. I found that interesting. Can you comment any if you were expecting that?
Yes.
In your results?
I think it was interesting, but I don't think it was so like unexpected. Since we expect the tumor to change in size, the area right around the tumor is the area it's going to expand to or like shrink. So that area itself is actually really important as much as the tumor itself. So I also thought it was interesting, but this was something that we kind of wanted to explore because we thought it would have an effect.
I'll make a comment that it sounded, how to say this, like you just said, it sounds intuitively correct, but it's much better to have done what you did, which is the extra step of let me prove it by comparing with and without in the models and demonstrate that there is signal in that paratumor region.
Right.
Thank you. That concludes the questions I have at the moment.
Thank you.
Thank you, Curtis. Let's go to Olash. Olash, do you have questions?
Yeah, so the field is so fast, right? So all these algorithms are converging nowadays into this jargon everybody use, foundational models. So do you think you can combine this imaging part with radiology reports to repeat your study and have the similar, maybe even better, the results? What are the difficulties of creating a foundational model for your project?
Mhm.
What do you think? Like, how you can extend this to something like more unsupervised, large scale, feature extraction, and then applying to your settings?
Exactly.
What are the difficulties? What are the advantages?
I think that's a really good point. If we were to have those radiology reports, we can actually learn from those reports and just have them match the imaging that we have at the moment. And also, if we have those reports at different times, we can also see how the imaging changes and then how the reports have changed to explain the changes in the images. So we can kind of like track what is going on with using some NLP methods to understand from the reports. We can extract some keywords, let's say, or we can look how they are describing what is in the image. So we can have a better understanding on understanding the tumor itself rather than just using image processing. Other than that, we can also use it as a way to make the models more explainable. So when we are giving an outcome, we can also create these reports ourselves as an extra output. Just like we are giving some like uncertainty outputs with the prediction itself, we can also create these reports.
So what is the difficulty in front of creating such a system, foundational model for medical imaging in general and particularly for your project?
I think the difficulty would be similar to the data that we're using right now. In the reports, we would have a lot of ambiguity coming from different doctors. So being able to just evaluate them, correct or not, can be one of the challenges that we might have. Other than that, just if we were to have them over time, like multiple reports for the same exact patient, just having that data aligning can be another challenge. But yeah, those are two that I can think of right now.
So in radiomics works, so theoretically, deep learning algorithms, when you use, it should cover the feature sets and the features which are defined by radiomics.
Right.
However, when you combine deep learning features with radiomics, it seems your results are improved. Does this tell us your radiomics features are not covered by your deep learning features? Or so what's going on there? Why the results are improved? Is your deep learning algorithm not capable of getting those hand engineered features?
I think the reason why behind this is because with radiomics, we are measuring the tumor's features itself. But with the neural network, since we are giving the whole CT image or the crops, we are also learning some of the global context that is not only in the tumor region. So that gives us better insights, and the deep learning model can understand more complex patterns compared to the radiomics. So they both work okay, but when we were to combine both of them, they kind of complete each other in that sense. And another thing would be radiomics features. If we were to just include all of them, there's also a lot of noise that doesn't really help us with the outcome prediction. So just reducing those features to the ones that we need is a really hard task because it can also hurt the performance rather than improving it if we're adding a lot of noise.
Okay, thank you. I think I can give the questions to others now because we will ask again, right, David?
Right, yeah. Damla, I'll skip you for now. Let's go to the public audience. Do you have any questions?
Okay, mine is really fairly simple. I expected late fusion to be better, but there's some advantage in looking at a hybrid where you do early fusion and late fusion, and then what you do is look at them for increasing your confidence level and looking for areas of lower confidence. Have you thought at all about that?
Yes, so when I was using the feature selection models, I would look which features were affecting the outcomes the most, and then that was my way of looking at uncertainty when picking the features. So I applied that to radiomics features. I haven't applied that to deep neural network features because I use both PCA and lasso for feature reduction. But the way I reduced the features for the radiomics one was exactly looking at that.
Okay.
How much they correlate, yeah.
Thank you.
Yes, thank you.
All right, so thank you again, Charlie. So let's now go to the private session. Everyone will be asked to hang up, and thank you so much again for showing up for Ilkin's presentation. Ilkin, make me the host.
Yep.
And stop the recording.
And I'll just say that was a great presentation. Thank you.
Thank you so much.
Thank you so much, Charlie. We'll see you soon.